Okay, this is the last part of our review, part 3, circular motion and projectiles. So, these are all the things that we went through. I'm going to take a couple of notes first. So complete all the things. So before we can jump into that, we need to know what the period is. We use T for the period. That's the time for one revolution. Frequency is sort of its inverse. It's the number of revolutions per unit time. The period is equal to 1 over the frequency. The frequency is equal to 1 over the period. This is useful because we can calculate velocity with these things. If we're moving in a circle, the distance around the circle once is the circumference, 2 pi r. And if we divide that by the time it takes to go around the circle once, it's going to give me the velocity. Or I could use frequency to calculate that. 2 pi r is the distance in a circle, and t is the time it takes to go around the circle once. And then centripetal acceleration is v squared over r. That's any time we move in a circle, we have this acceleration. And this is really important, right? So if we're moving at a constant speed around a circle, we're going to have centripetal acceleration. Because anytime we move in a circle, we're accelerating because the direction of our velocity changes. So these are kind of the things that we're going to use to go through circular motion stuff. So let's look at part A, find the period and the frequency of this bucket. So, the bucket makes 2 revolutions each second. That's telling me how many revolutions per unit time. My frequency is 2 revolutions per second. The period is the inverse of that, so it's 1 over the frequency, 1 over 2, so it's half a second. If I want the velocity of the bucket, it's going to be 2 pi r over the period. So 2 times pi times 0.75, because that's the radius, divided by the period of 0.5 seconds. That makes my velocity 9.42 meters per second. Now I want the force of tension in the string. Now we haven't talked about force yet, but if we're in a horizontal circle, the net force is just the tension. That's the only force acting on my object. And that's also equal to mass times acceleration. But the acceleration I have is centripetal acceleration. So that tension is going to be equal to the mass times the velocity squared over the radius. Because I'm moving in a circle, that's the acceleration I have. So it's going to be the mass, 0.8 kilograms, times the velocity, which we just found, 9.42 meters per second. And we're going to square that 9.42 divided by 0.75 meters. So we put that on our calculator, and we see that the tension is 94.6 newtons. Part D, Dale notices that when he swings the bucket in a vertical circle, the water doesn't fall out when the bucket's at the top. So with this, the water at the top is moving horizontally. It's moving sideways, not down. It's moving sideways because objects want to move in a straight line unless a force acts on them. And the velocity at the top is pointing sideways, so the object is moving sideways. The bucket pushes down on it, turning it, but it doesn't fall out because it's not moving down, it's moving sideways. The bucket pushes it straight down to turn it. So when we're at the top, our velocity is tangent to the circle, moving sideways. E is sort of a continuation of that. Force is down, velocity sideways. If I cut the string, the object will continue moving in a straight line. The bucket would move in a straight line with its velocity. Tangential to the circle, that's the moving in a straight line, off like that little V line is drawn. Draw a diagram showing the force, acceleration, and velocity vectors while Dale is swinging the bucket. So if we look at that, all around the circle, the velocity is going to point tangent to the circle. The tension is going to point in, and the acceleration is going to be in. Those are my forces. The acceleration, when we're moving in a circle, always points to the center. That's an important thing for the acceleration. It always points to the center. All right, so down here with number 2, doing a projectile problem. We're launching a cannon from the top of a 45-meter tall cliff with an initial velocity of 57 meters per second. Is this a projectile? You bet. The only force acting on the cannonball is gravity as soon as it leaves the cannon. That's our condition. As soon as it leaves the cannon, the only force on it is gravity. That's what makes something a projectile. In which axis of motion is the velocity constant? That's on the x-axis. There are no forces in the x direction to accelerate the cannonball. So with no x forces, there's no x acceleration. And with no x acceleration, that velocity is constant. Nothing to change that velocity. So the velocity in the x direction stays at 57 meters per second. So if I want a free body diagram of the cannon after it's been fired, while it's in the air, with part A, we said the only force acting on it was gravity. So that's it. That's a free body diagram. There's one force acting on it, and it's the weight. Draw a motion diagram showing velocity and acceleration for the cannonball as it's in the air. So it's going to follow that path. The velocity in the x direction stays the same, but the velocity in the y increases because it's accelerating in the y direction. So we need to see that velocity in the y getting bigger. And the acceleration is always down. The velocity in the x is constant. The velocity in the y increases because we have a downward acceleration the whole time. So we want to calculate the time that the cannonball is in the air. That's only concerned with the y information. If we look at our y information and list out our knowns, we know that the acceleration is gravity, and it's just 10 meters per second squared. We know that the initial velocity is 0. All of my initial velocity is in the x direction, not in the y direction. We're only concerned about the y direction. And then the delta y is 45 meters. I want to know the time. So I want the equation with all 3 of those things in it. Delta y equals v0t plus 1/2 at squared. But since the initial velocity is 0, we're just going to cross that out. So 45 is equal to 1/2 times 10 times t squared. So in order to get t isolated, we're going to multiply both sides by 2. That gets rid of the 1/2, and divide both sides by 10. So we have 2 times 45, that's 90, divided by 10, that's 9, is equal to t squared. So we square root both sides, and the time is 3 seconds. Calculate the horizontal distance the cannonball travels before hitting the ground. Well, that's an x direction problem. In the x direction, the initial velocity is 57 meters per second. The acceleration is 0 because there are no x forces. The time is 3 seconds. And I want delta x. We're going to use the same equation, delta x equals v0t plus 1/2 at squared. But since the acceleration is 0, that whole side goes away. And our delta x is 57 times 3. That's our review. Good luck studying for your test.